this chart is about uniform circular motion, UCM, velocity and acceleration. So to start, uniform circular motion is what occurs when a particle moves on a circle of radius r at a uniform angular rate. And so the convention is to take counterclockwise, which is the direction my mouse is moving here, as positive, and counterclockwise is positive. Okay, that's this direction, and clockwise is negative. So that would be that direction. So to mathematically describe this, what we'll do is we'll have a circle of radius r. We'll put x and y axis through the center of the circle, and we'll draw a radius vector from the circle center to the instantaneous position of the object. And at that instantaneous position, you have this vector r vector, which is the position vector, and it's inclined at an angle theta with respect to the horizontal, which is changing uniformly with time. So look up here on the left, theta equals omega t. Omega, Greek letter omega, is the angular velocity. And omega is constant. If I take the time derivative of theta, I get omega, and omega conceptually has units of rads per second. Once around here, corresponding to 360 degrees, corresponds to 2 pi rads, and so the angular velocity omega is clearly 2 pi rads divided by big T seconds. Big T is the period. It's how long it takes the particle to go around the circle once. Okay, so we want now to talk about the velocity vector and the acceleration vector. We've talked about the position vector already. That's the vector that points from the center of the circle outwards, this black arrow that you see here. So we can describe this position vector as its projection on the x-axis, our cosine omega t, times I hat. Recall that I hat is the unit vector in the x direction, plus r sine omega t. That's the projection of this same position vector onto the y-axis, times j hat. And so more or less mimicking the picture here, if this is the r vector, this would be r cosine omega t I hat, and this would be r sine omega t I hat at this particular instant of time. So now let's look at v, the velocity. And so velocity is time derivative of position. And so if I differentiate r, I hat and j hat don't change. They always point in the same direction. And so the derivative of r vector is basically just the derivative of the x component times I hat, which is minus r omega sine omega t. So the derivative of cosine is minus sine, and from the chain rule, we're going to spawn an omega here. So a negative sign creeps in, and then the time derivative of the y component is r omega cosine omega t times j hat. So if you look at geometrically what's happening here, essentially, if you think about comparing the v vector to the r vector, the comparison is that the x component of the y vector is the negative of the y component of the r vector times the constant, and the y component of the v vector is the x component of the r vector times the same constant. And so that's what I've done in this picture here. So I've taken this vector, the y component, and I've changed it into the x component, but I've made it negative. And then the y component, now I've taken the x component and put it up like that. So I've switched the x and y components and made one of them negative. And I get a overall v vector which points this way. So if you look at the r vector here and the v vector here, you will see two things. First of all, that the v vector is perpendicular to the r vector, and that the v vector is pointing in the direction of increasing angle. This is a geometric argument. All right, so let's move on to the a vector. And I've drawn it that way here. So you can see the v vector is drawn in the direction of increasing angle and drawn so that it is perpendicular to the r vector. What about the a vector? Well, to get the a vector, I'm going to differentiate the v vector. And so if I differentiate the v vector, I get, well, okay, so if I differentiate sine omega t, it's going to be omega times cosine omega t, and so I'm going to end up with minus omega squared r cosine omega t times I hat. And if I differentiate cosine omega t, I get minus omega sine omega t, and so the j hat component is going to be minus omega squared r sine omega t. So clearly I can pull a minus omega squared out, and it's minus omega squared times r cos omega t I hat plus r sine omega t times j hat. But the quantity in parentheses is just r vector. And so the really cool result here is that the a is minus omega squared times r. What does that mean? Well, it means that it is anti-parallel to r, pointing inwards, in other words. And this is what we call the centripetal acceleration. All right, so let's summarize what we've done here. We have found that v is tangent to the circle. It points in the direction of increasing theta. And we've also found that v is equal to, magnitude of v is equal to a constant. V itself is not equal to a constant because it's changing direction. So v magnitude is magnitude of this vector that we found up here. And Pythagoras tells us that this is just going to be the sum of the squares, square root of the square of the sum of the two of its x and y components, the square root of that. And that's what I get if I do this. So r omega is equal to a constant, which is equal to the magnitude of the speed, constant speed of this particle moving around the circle. We've also found that a vector points inward. That's the centripetal acceleration. And the magnitude of a is simply r times omega squared. And that is equal to a constant. I'll let you demonstrate to yourself that r times omega squared can also be expressed as v squared over r, over big R. You can show that for yourself. And furthermore, we've shown that a vector is perpendicular to the v vector. You can see that from this picture. So here's the v vector and here's the a vector. So they're perpendicular to each other. And the geometric result of that is, since there's no component of a in the direction of v, the magnitude of v doesn't change, but the direction of v changes. And so a is always being perpendicular to v means the magnitude of v doesn't change, only the direction does.